I'd like to show several announcements to you. So please carefully look at these two instructions and follow these instructions. And also, I need to mention that in this AIP Open Seminar, we will record the seminar. And later, we will upload that movie to the some website in AIP. So this is these are the formal announcements. Okay, so let's start today's AIP Open Seminar. And today, the topological data analysis team will give 3 talks. And I'm Hiraoka from Kyoto University and AIP Riken. I'm a team leader of the TDA team in AIP. And I will briefly give an overview of the topological data analysis by using the 25 minutes. And after that, Ippei Obayashi will give a talk about TDA with machine learning, software, and several applications. And the final speaker, Emerson Escala, will give a talk about the applications of the mapper to the economics problems. So we hope you will enjoy these 3 talks today. All right, so let's start my part. And well, basically, in my talk, I will focus on the mathematics part of the TDA. In particular, I will focus on the persistent homology. But before that, let me briefly explain what the TDA means. Well, TDA is an abbreviation of the topological data analysis, and it is developed in this century. And it is developed for analyzing the massive and complicated data by using topological tools. And it is trying to characterize the shape of those massive and complicated data. And well, the mathematical and algorithmic studies of TDA has been very actively studied recently, but in parallel, those concepts and tools have been applied to the various fields of the applications, practical applications, and some of them are listed here. For instance, our team has been applied TDA to the material science, and it has been applied to the neuroscience, genome analysis, and then protein structure analysis. And also, it has been applied to the so-called sensor network problems, and in more general, it is applied to the big data analysis, including social network, healthcare, stock market, image analysis, etc., etc. So now those TDA has been applied to the wide variety of practical problems, actually. And as I said, our team has been applied TDA to the materials science so far, and these are some of the projects to which we have applied TDA so far. And today I will not go into the detail of them, but as here you see some of the diagram like this, or like this, and then like this. There's some plots above the diagonal. Those are the persistence diagrams. And in my talk, I'd like to explain what the persistence diagram is and how to apply it to the practical problems. All right, so this is the background and the motivation of my talk. And now these are the agenda of my talk today. So first, I'd like to explain some geometric models for data and introduce persistent homology and persistence diagram. And then we have 2 more topics, number 2 and 3. All right, so let's get started the geometric model of our data. So for the sake of simplicity, and actually I don't have much time today, I only focus on this type of input data called point cloud data, X. This is just a finite point in a space. So we can, of course, deal with, say, time series data or digital image data, etc. for TDA, but today I will focus on this type of data called point cloud data, such as atomic configurations, sensors, etc. for the practical applications. And given such a point cloud data, Then the first thing we need to do is to build a kind of geometric model in order to characterize the topological or geometric structures embedded in this data. Since those are just discrete points, we need to somehow build some geometric model to study its topology. And for that purpose, we sometimes use the check complex. Check complex is just a polyhedron, or mathematically speaking, it is a simplicial complex. And the definition is given by this. This is the vertex set is given by the point cloud X, and the rule to add these k plus 1 subset is defined by this rule. Well, here BR means a ball radius R with radius R centered at this point and checking the intersection of them. So this is the definition of the check complex, and it may be not easy to imagine what the check complex is actually from this mathematical definition. So let's go to the example to see what the check complex is. So suppose we have these two types of point cloud data, 3 points and then 3 points here. And then we put the radius R ball at each center. Then the check complex is given by given by this respectively. Namely, the vertex set is given by the same 3 points, and the rule to add edge between these 2 points is to check the non-empty intersection of the balls. So since we have this part, since we have the non-empty intersection here between these 2 balls, we assign an edge here. In the same rule, we have an edge here and we have an edge here because we have an intersection here and then here. Similarly, we have 3 edges here. And the next, the rule to add the triangle is to check the non-empty intersection among these 3 balls from this definition. So to check the non-empty intersection of the triple balls. And since we have a non-trivial intersection here, we assign a triangle here. On the other hand, in the right-hand side, we don't have triple intersection, so we don't assign triangle here. So this is an example of the check complex. I hope it helps you understanding. Then, from this example, you are observing an interesting phenomenon, namely the existence of hole in a ball model and the existence of hole in the check complex are corresponding to each other. It means that if you have a hole here in a ball model, you have a hole in the check complex and vice versa. And this observation can be generalized in the so-called NAV theorem. This is a classical theorem in algebraic topology. And it says that the radius R ball model is homotopically equivalent to the check complex with the same radius parameter R. And note that the check complex is dependent on the parameter R, which is appearing in here, controlling the radius parameter. And it says that the left-hand side and the right-hand side are, in a sense, the same. Here, you don't need to know the definition of the homotopy equivalence. It simply says that you can continuously deform between left-hand side and the right-hand side without cut and paste. In particular, it preserves the whole information. And recently, this theorem is regarded as an important theorem for practical applications because usually in the practical applications, the left-hand side is our interest. For example, in the material science, left-hand side can be regarded as a ball model of the atomic configurations for materials or say proteins and so on. So X is specifying the location of the atom, and R can be regarded as a ball of the atom, for instance. Or if you are interested in a sensor network, X can be regarded as a location of each center, and the R can be regarded as a sensing radius. So the left-hand side is expressing the covering region or sensing regions. And if you are interested in such a region or atomic configurations, then you first go to the check complex and study its topological structures. Then the result obtained in the right-hand side is precisely explaining the left-hand side because of this NAV theorem. So it guarantees that there's no loss of information in the topological sense between left-hand and right-hand side. And the point is that the right-hand side is easy to treat in computer. So we can do such a topological analysis in the right-hand side very easily. So actually, in the practical application, we use this NAB theorem to study our interest, left-hand side. All right. So as we see, the check complex is dependent on the parameter R appearing here, controlling the ball radius. So if you have S greater than R, we have this inclusion. Since check complex is checking the non-empty intersections, and intersection is a monotone properties with respect to the radius. So by gradually increasing the radius parameter R from 0 to very large number, you will get a filtration, or you can call fattening sequence like this. Zodaides, fattening sequence. So in this sense, the parameter R can be regarded as controlling a resolution of our data. Actually, this way of understanding will be useful in later discussion. All right, so this is the essence of our geometric model. Then from this slide, let me briefly explain an idea of persistent homology. This slide is just for a very idea. So suppose we have this kind of input data like this, point cloud data. Then in persistent homology, we do not directly study these point clouds data, but we consider an increasing sequence of balls like this, patterning sequence of balls as before. And then in persistent homology, then we observe that the blue hole appears around this radius parameter. And you also observe that this ball will disappear when you increase your radius slightly. In persistent homology, we try to characterize, or we try to record this appearance and then disappearance phenomena algebraically. And also you see that around this radius parameter, red hole also appears, which seems to be more robust with respect to perturbation comparing to the blue one. And persistent homology is also characterizing such a difference between red and blue holes. This is the idea of the persistent homology. And I'd like to emphasize that we are artificially changing our resolutions or radius parameters. It means that persistent homology is good at a kind of multi-scale analysis problem. So we can change the scales. Then this slide tries to explain persistent homology and then persistence diagram intuitively. So suppose we have an input data like this, the atomic configuration, or more generally point clouds data today. Then persistent homology will output the information of shape of data. In particular, it characterizes holes in data, and it describes number, size, and the shapes of those holes, and it is good at multi-scale analysis. And more precisely, persistent homology outputs the so-called persistence diagram, like this figure. There's some plots above the diagonal on the plane. And for the practical purpose, persistence diagram is used for the practical applications. So you need to know the meaning of the persistence diagram for that practical purpose. And in the below, I'm showing how to construct persistence diagram, which will help you to understand the meaning of the persistence diagram. So suppose, again, just for simplicity, suppose we have these 4 points. Then we put a ball as before, like this. Then as before, we gradually increase those radii from very small to very large. Then at this specific radius parameter, say B, hole appears, and we record this specific radius parameter B as birth. And further, we increase the radius parameter, and at this specific radius parameter, say D, this corresponding hole disappears, and we again record this radius parameter, specific radius parameter d as this. Then we plot this b and then d on a plane here, and the persistence diagram is a collection of all these birthday pairs appearing in our data. So this is an intuitive understanding of the persistence diagram. And from this construction, for instance, if you have these diagrams, it tells us that we have 5 holes in our data, 1, 2, 3, 4, 5. So each point called generator in persistence diagram expresses a hole in data. And also, birth and then death axis measure shape of holes. And more importantly, we can mathematically prove these 2 statements. The first statement is that point or hole close to diagonal like this or like this can be regarded as noise, in the sense that if you add some small perturbation to your input data, these generators can disappear. On the other hand, next statement, if your point or generator or hole is away from diagonal like this, it can be, it is more robust. It is very robust in the sense that even if you add some perturbations to your input data, this generator will be stable. So we can prove such a statement mathematically. It is called the stability theorem of the persistent homology. And also, I'd like to emphasize that the inverse analysis is also available in persistent homology, which is very much important for practical analysis, including materials science, by which we can directly study the input data structure or atomic configurations from the persistence diagram. I just mentioned it here. All right, so this is the essence of the persistent homology and the persistence diagram. And in this slide, I would like to briefly explain the same concepts mathematically or for the audience in the mathematics community. So suppose we have a filtration X from X1 to Xn, then the persistent homology is defined by a sequence of homology vector space by taking homology on each slice connected by a linear map induced from inclusion. So this is just a sequence of the vector spaces and the linear maps between them. So it can be regarded as a representation on AN quiver. Then in such an algebraic object, we have a nice property called interval decomposition or structure theorem of the persistent homology. It says that for any persistent homology under a mild condition, it can be uniquely decomposed into the direct sum of the interval representations I. Here, interval representation I from B to D is defined in such a way that we have one-dimensional vector space here from XB up to XD connected by the identity map and 0 otherwise. Topologically speaking, this means that we have one hole appears at XB somewhere. It will persist up to XD, and that hole will disappear after that. So this is the meaning of the interval representation. And since we have a unique decomposition, the persistence diagram is just a collection of all these birthday pairs appearing in this decomposition. And usually it is plotted on a plane like this. So this is the persistent homology and the persistence diagram. All right, so now I'd like to move on to some generalization of the persistent homology and the persistence diagram using quiver representation today. And from this generalization, this generalization enlarges a range of applications very much. So I'd like to explain that aspect in this section. All right, so let me remark that so far, our input data is implicitly assumed to be static. It means that our point cloud data does not move, just a static one. That was assumed implicitly. But in the practical applications, we frequently need to study time series data like this. It means that our point cloud is dependent on time t, such as protein foldings, polymer deformations, or moving sensors, etc. So let's think about this problem. Then, even in this situation, at least we can construct a time series of check complexes by fixing radius r. Namely, by fixing radius r, for each time t, we have a point cloud, so we construct a check complex at time t. Then we have a series of check complexes. However, that series will not be a filtration in general. It's just a time series of the check complexes. And let's recall that in the formulation of the persistent homology, we needed an increasing sequence of the check complex or balls. So filtration was necessary in the original setting, but this sequence is not filtration in general with respect to time t. So we need to consider some modifications. And one way is to consider this kind of zigzag sequence. Namely, we embed Ct and the check complex at t plus 1 into the union of them. Then we will get a zigzag sequence of the check complex like this. Then, by taking homology, we will get a sequence of the vector spaces. In this setting, the linear maps are zigzag, are pointing to zigzag. Even in so in the original setting, the linear maps are all pointing to the right, but this case, the orientation is a zigzag. However, even in this setting, even in this zigzag setting, we have a same structure theorem. So same structure theorem is valid. It means that this persistent homology or sequence of the vector spaces can be uniquely decomposed into the direct sum of the interval representations. This property is guaranteed by the general theory of the quiver representations. And unfortunately, I will skip all of them today. But the point here, I'd like to emphasize that we can do the same decomposition property here. And this will allow us to study the persistent topological features in time series sense. So it means that we can study time series, we can study the persistent topological features appearing in a time series by this way. I will skip all the detail of the quiver representations necessary to explain this. So it looks nice. So we can study time series data, but there is one drawback. It means that in this setting, the spatial resolution R is fixed, and persistent topological features in spatial sense cannot be studied. So what's next? Of course, we want both. It means that we would like to study the spatial and temporal topological features, not only space, not only time, but also both. So this motivation gives us an interesting mathematical question or problem called persistent homology with multi-parameters. Actually, persistent homology with multi-parameters is one of the frontier of the mathematical study of the persistent homology now. And several members in my team, TDA team in Riken, AIP, are also trying to characterize this mathematical object. Well, this is not an easy target, but there are several approaches. The one way is to use a so-called Grevner basis. But as you may know, the Grevner basis requires huge computational resources, and sometimes it is difficult to apply it into the large-scale problems. So in that sense, we need more modifications or another approaches maybe. And also Emerson Escala, so third speaker of today, and I myself proposed the so-called persistence on commutative ladder like this. We don't consider we don't consider full version of the two-parameter persistent homology, but only two steps towards the vertical directions like ladder. Then we have applied the so-called absolute latency theory for decomposition theory, mainly length n less than or equal to 4. And even in such a restricted situations, we could apply that into some problems in material science, and it worked pretty well. So although there are several other approaches, but because of the time restrictions, I will stop here to explain that directions. So, but I'd like to say that there are many interesting mathematical problems in multi-parameter persistent homology. So anyone who are interested in this topic, is very much welcome to join. All right, so my time is almost over. So I will briefly mention the connection between machine learning and persistence diagram. The detail will be explained by Ippei Obayashi, next speaker. So I will briefly introduce some aspects. So first, recall that a persistence diagram is just a collection of the basis pairs. So in order to apply machine learning standard machine learning methods, we need to first vectorize persistence diagram some way. And to that aspect, we have obtained very roughly speaking, we have obtained two types of result. The first result is under collaboration with Fukumizu-san in Tosuken and Genki Kusano. Here we developed the so-called persistence-weighted Gaussian kernel, so kernel method for persistence diagram, and used this structure for vectorization. And the second result is about the linear machine learning models on persistence diagrams, which will be explained by Ippei. And we have also developed a software called HomeCloud. This will also explained by Ippei, I think. So if you are interested in this software, please visit this website. Then you can freely download it. Document is also available, and then you can enjoy the software. All right, so this is the end of my talk. So thank you very much for your kind attentions. And now I pause a few times waiting for your questions and comments. So if you have any questions or comments, I think you can freely unmute. I think you can do that. If not, please write your questions in the chat or use the raise hand feature.
I have a question. What is the computational complexity of persistent homology, or drawing a persistent diagram? Can we have like the number of points in the number of millions? Sorry.
It's a good point of the. It's a good point. Well, in the sense of the computational complexity, it is dependent on the say n cube. N is the number of the point, for instance. But we usually compute the persistent homology first by reducing our problem into the very small size. So usually n will be very small. So in that sense, at least in my experience, the computational speed is very fast. For instance, even if you have, say, thousands of points or 10,000 of points, we can quickly compute the persistence diagram.
And what about, does the ambient dimension of the point cloud, does it matter? Like if it's very large, do these balls have a hard time intersecting with each other?
I see. It's also a good point. Well, I skipped all the details because that was a time restriction. But I can answer several ways. Yes, in general, yes. If you have a very large ambient space, then the computational cost will increase. But in that case, we will change our geometric model. So today I only introduced the check complex. It will take so long time because we need to check the many intersections. Then in such a case, we replace it with the so-called Rips complex. And the Rips complex is defined similar way, but it is just checking the pairwise intersections, not all intersections. It means just if you have, say, distance matrix, you can easily compute that. That will drastically decrease the computational cost. even if your ambient space is very large.
Thank you. Thank you very much.
Thank you very much for your question. I have another question. I will call that question. So in the example of molecules, not only their topology, but also angles in between edges are crucial. Is there a notion of the check complex as a metric space to see those angles? The first easy answer is no. No. A check complex itself doesn't deal with such an angle information, I think. But as I explained in my talk, in persistent homology, we have an inverse analysis. This is a really important tool to study your question. Namely, once you have some interesting generator or hole, you can click this point. Then you will get an original subset of the point cloud, which actually generates the corresponding hole. From that information, you can easily study or check the angles, for instance, if necessary. So for that purpose, inverse analysis is really important. And I'd like to advertise. Sorry. Yeah, this software can deal with that. I hope it will answer to the chat question. Okay. All right, so now time is already over. So I'd like to move on to the next speaker.
Okay. Thank you for introduction. Okay. I'm Hiraoka, working in looking AIP. In this talk, I will talk about the practical aspects of persistent homology. Before talking such a topic, we introduce myself. I'm Hiraoka. I'm a research scientist in looking AIP, working on topological data analysis. I'm an applied mathematician, and I'm mainly interested in topological data analysis, especially persistent homology. I'm interested in theory and application of persistent homology. I also developed a homology persistent homology-based data analysis software. And my another interest is dynamical systems. Okay. This is topics today. Yeah. I introduce persistent homology briefly, and I will talk about some of these topics. Machine learning, application to material science, and software, and inverse analysis called optimal volume. This is an example of persistent homology analysis. Do you find any characteristic difference between these two blocks, left 4 figures and right 4 figures? This slide shows the answer to the question. In fact, the right 4 figures have finer or smaller structures than left figures. And blue points indicate typical geometric structures for the left 4 figures, and red points indicate geometric structure for right 4 figures. Red points are located on small islands like this, small islands or small peninsulas. Such structures are more typical in the right figures. We can automatically find such a structure by using percentage homology. Now, I review the idea of percentage homology briefly. Yeah, percentage homology is one of the most important tools of topological data analysis. Data analysis methods using mathematical idea of topology. And topological data analysis quantitatively characterize the shape of data by using connected components, rings, cavities, and other topological structures. And percentage homology uses the idea of homology, one of the most important research field in topology. And percentage homology gives a good descriptor or feature values for the shape of data called persistence diagram. Persistence diagrams are already shown in the previous presentation. And percentage homology is developed in this century very quickly from mathematical theory and algorithm to and software to application to various fields of science. For example, material science and life science. Yeah. Now I quickly review the percentage homology and persistence diagram. We consider the point cloud, the left field, as an input data. This is the set of points. And the point cloud has no holes or rings, yes, but the point cloud looks like some have some holes. So to construct such a topological structure, we put disks or balls with ready R. And we can find 3/4 in the right field. And the theory of homology can count the number of holes. The problem here is how to determine the ready of balls or disks. In the theory of percentage homology, we consider the increased sequence or increased process of balls instead of determining one ball size. In this figure, the radius R becomes larger. Some holes appear and disappear like this from the left field to right field. And the theory of percentage homology make pairs of the appearance and disappearance of holes. In this figure, a hole appears at R2, disappears at R5, and a hole appears at R3, disappears at R4. So we make two pairs of birth and death, appearance and disappearance of the holes. And these pairs are called basis pairs. And the scatter plot or histogram plot of these pairs is called the persistence diagram. we use this diagram to capture geometric structure of the data. So now I explain how to combine Parsons homology and machine learning. This slide shows the fundamental idea of the combination. Parsons homology can summarize the geometric structures of the data quantitatively, and machine learning methods can find characteristic patterns from the data. So the combination of these two concepts, we can extract characteristic geometric pattern from data. This is the fundamental concept of the combination. Now, today, I present a method which is good for the explanation and interpretation. Normally, machine learning mainly focus on the prediction, but in today's talk, we will focus on data explanation and interpretation. This figure shows the standard framework of the combination of Parsons homology and machine learning. As you know, almost all machine learning methods accept vectors as an input data. So, to apply the machine learning methods to Parsons scenario, we need to convert an input data into vectors. And for good performance of the learning, we need to construct a good vector. Good vector means that the vector has important features of the data. So how to construct vectors is important, and many methods for vectorization are studied now. And this is our framework of the combination of Parsons homology and machine learning. The upper half of the figure are almost the same in the previous slide. The difference between the previous figure and this figure is the arrows from right to left. We use inverse analysis to map random pattern to the original data. This is a joint work with Hiraoka-san and Kimura-san. Okay, I explain this framework. This is a list of already proposed vectorization methods. In this slide, 7 methods are shown, and other methods are also proposed now. And in this talk, we use one of them, a persistence image for vectorization, and we use linear models for machine learning models to enhance or improve the interpretability of the learned results. This slide shows the this slide explains the persistence image, one vectorization method. This method is proposed by Adams et al. In 2017. And yeah, in this method, the histogram of one PD is regarded as a vector. And this is very simple, a simple idea. And we use two techniques to improve the results. One technique is Gaussian density estimation, Gaussian kernel density estimator. And another is the importance adjustment by using weight function, weight value. Yeah. Now we consider the a function or a distribution on the plane, on xy plane, like this. Yeah, this is a weighted sum of Gaussian distribution, and each and the center of Gaussian distribution are basis pairs. Here, in this equation, equality, n is the Gaussian distribution whose standard deviation is sigma, and W is defined defined by the arctangent function. This W is a weight, and this weight function is used to reflect the importance of basis pairs. Yeah. In fact, in theory of persistence homology, basis pairs near the diagonal are less important than other basis pairs. This omega is used to reflect such an importance. And this distribution rho is discretized by grid. And yeah, such a discretization can be effectively computed by using Gaussian filter. This slide shows an intuitive explanation of persistence image. The Gaussian distributions are located on each basis pairs, and the height of Gaussian is changed by from the depending on the distance from diagonal line. The Gaussian distribution near the diagonal lines are small than other distributions. And now we use logistic regression, classical to classification problem, classification tasks. Yeah. Data input data of the logistic regression is a pair of vectors and 0-1 value. And the goal of this logistic regression is to find the relationship between x and y from the data for the finite number of data. So, to find such a relationship, we need model to we need a mathematical model. In this model, we assume that following probabilistic relationship between x and y, and appropriate vector A and B are estimated from the given data. Yeah, this process is called learning. And to combine logistic regression with persistence homology, persistence image vector explained before is used as vector x, like this. From the definition of Parsons image, the inner product in logistic regression model is L2 inner product on the function space on the plane. Yeah, the probability of y is equal to 1 is shown like this. Here, A of xy is the round vector, and from the expression, the integral, this integral means the importance of each basis pair, bi di. And this means, if this integral is positive and large, the corresponding basis pair has a large contribution to the probability of y is equal to 1. And if the integral term is negative and its absolute value is large, the corresponding basis pair has a large contribution to the probability of y is equal to 0. And if the absolute value of the integral is small, the basis pair does not contribute the probability. By using such an idea, we can identify the important basis pairs for the classification. And other pairs have less information. It means that other pairs have less information. So we can, so after identifying the important basis pairs, we can apply the inverse analysis to find the original geometric structure corresponding to such basis pairs. So by using inverse analysis, we can map the round pattern to the original data. This is the whole. This is the total framework of our methods of combination of machine learning and patient homology. Skip this slide, and next I will explain some two applications of persistent homology to material science. One application is the credit formation of glassy polymer. This is a joint work with Chinomiya-san and Hiraoka-san. And the paper is published in 17. The purpose of this research is the analysis of credit formation of glassy polymer. The polymer in this study, the polymer is numerically simulated by using molecular dynamical simulations. In the simulation, polymer is modeled by the chain of balls. The real polymers have such a structure. Polymer consists of many monomers, many small small molecules, and such molecules are connected like a rope or chain. And in this simulation, the polymer is deformed, and by the deformation, many small buoys are generated, and such buoys becomes larger, and finally, the polymer is completely destructed. We want to analyze the process of the destruction of polymers. So the problem here is to identify the clays, small buoys. Polymer is modeled by the chain of balls, so it is not an easy task to identify the small buoys in the simulation data. So for that purpose, we use persistence homology. In these figures, we can identify many buoys by using persistence homology, like this. Red are small buoys, and such buoys become larger. And finally, we found that large buoys are generated by gathering columns of small buoys. We call the phenomenon buoy percolation. This is the result of our application work of persistence homology. This is another application of persistence homology to material science. This is a joint work with Hirata-san, Wada-san, and Hiraoka-san, and the result will be published in Communication Materials. The target of this research is a metallic glass. Metallic glass is a metallic material with atomic level disorder. And metallic glass consists of the mixture of various atoms. And the atomic configuration is computed by molecular dynamic simulation. And the materials cool down very quickly, and such a fast cooling makes disordered structure called amorphous or glass. And some cooling rates are computed in the simulation. We call them slow cooling glass and fast cooling glass. And material science believes that the faster cooling makes more distorted or disordered structures. The purpose of this research is to show that to prove that such ideas. This is a setting of this research. In the molecular dynamic simulation, we use the atoms are PD, palladium, and silicons. And we compute persistence diagrams for PD atoms only, and Si atoms only, and all atoms. In this talk, I show two-dimensional persistence diagrams for PD atoms only. And in this study, we use machine learning with persistence image and logistic regression this idea is explained in the previous slide. And this is these figures show the results of the study. The upper right figure means that the distribution of dust pair, these diagrams are computed from fast cooling glass and slow cooling glass. This the upper left figure means that the distribution of basis pairs in the diagrams are considerably different from fast cooling data and slow cooling data. The peak of the distribution is slightly shifted from left to right by making cooling rate faster. And we picked a basis pair from here and here, and find the corresponding structure by using inverse analysis. These two shapes look like regular icosahedrons, but a bit somewhat different. And the right shape looks more distorted than left shape. To analyze such a disorder of these shapes, we examine the distribution of the areas of triangles in these shapes computed by the inverse analysis. And figure E, this figure shows the distribution, and we see that the distribution from slow data has a sharper peak here. And this means that the fast cooling data has more disordered structures. Okay, now I will go to the software of partial homology. For practical data analysis with partial homology, the software is important, of course. And in this talk, I will introduce homocloud, developed by our research group, mainly by me. This is data analysis software based on partial homology. Now, there are many software for partial homology. These software are developed depending on each researcher interest and analysis target. There are more than 10 software developed. And homocloud, one of such software developed by our research group. homocloud focuses on applications, and currently the current main target is material science. For example, molecular dynamic simulation data and images from electroscopy or CT data. Of course, we can apply our software to any other fields. In fact, HomeCloud internally uses Differ, FAT, and Lipser. These softwares are developed by by other groups. Is used for computing persistence diagrams, and we focus on the visualization, machine learning, and inverse analysis for practical application of persistence homology. Yeah, we can use HomeCloud for the analysis of two-dimensional or three-dimensional point clouds, or any dimensional image, binary images or grayscale images, and distance matrices. Yeah. These kinds, we can apply these kinds of input data. And inverse analysis is one important feature of HomeCloud. Yeah, all software, all persistent homology software can compute persistence diagram from point cloud data from here to here. But yeah, we often want to identify homological structures such as rings or cavities corresponding to each point on a persistence diagram. So our inverse analysis feature is I think most powerful compared to other software. And HomeCloud have two types of interface. One is a command line interface, and another is a Python interface. And you can utilize Python's semantic computing ecosystem with HomeCloud by using a Python interface. And you can download HomeCloud freely at this URL. Finally, I briefly explain the inverse analysis. Yeah, the task here is identify geometric structure corresponding to each basis pair on a persistence diagram. So, yeah, to find such a structure, we use optimization technique to find a minimal structure. Such an idea is called so-called homology optimization, and such optimization is now gradually become popular. Some researchers studied homology optimization like this. So now I explain why minimal homological. Why we want to compute minimal structure. In fact, one basis pair corresponds to many loops or cavities in the input data. And in the mathematical theory of homology, such many loops or cavities are combined into a single mathematical object called an equivalent class. So the minimal or tightest loop is best for intuitive understanding of a persistence diagram. And the problem is formalized as a optimization problem on homology algebra, and the formalized problem itself is hard to solve on a computer because it is a difficult combinatorial optimization problem. So therefore, the problem is approximated by linear programming and solve the problem by linear programming solver. And we can find such this kind of root. Okay, I stop my talk here. This is a summary of my talk. Thank you for your attention.
Thank you very much, Ippei. So any questions or comments to Ippei? So you can freely unmute and then directly ask him. If not, we will have a very short break, and the next speaker, Emerson, will give a talk from 4:15. So I think we have 2 or 3 minutes. Okay, so thank you very much, Ippei.
Thank you for your attention.
So hi everyone. So far we've been hearing a lot about persistence. Now, kind of to change gears, I want to talk about another tool in topological data analysis, and that's called Mapper. And in this talk, I will be using Mapper to study firms and their patent statistics, in particular to talk about innovation and the technological space of Mapper. So, hello, I'm Emerson, and currently I'm affiliated with Kobe University Graduate School of Human Development and Environment. But most of this research, or I should say all of this research, was performed while I was still affiliated at RIKEN AIP as a postdoctoral researcher. And the contents of this research are already available publicly in archive at this link. If you're interested, please consult this link. And this is a joint work with Hiraoka, Igami, and Ozkan. Okay, so let's dive in. So the motivation for this research is a very simple question. And that question is, where do firms innovate? And by where, we don't just mean geographical location. We also want to think about where in the sense of technological position, because we want to think like what sorts of fields firms are innovating or doing research in. And more than that, we want to see how they evolve over time, and how do they interact with each other, and do these locations, or does this point of view actually make any sense? Of course, we can think about these economic questions further down the line, but the first question that needs to be addressed is, how do we actually locate these firms in technological space? And that is what we set out to do, kind of like laying the groundwork for this point of view. Of course, there are other research in the economic literature tackling these sorts of questions, but I think we are the first to do topological data analysis of these sorts of questions. Right. So we want to map firms' locations, technological positions, but this is challenging. In the first place, when I say technological position, we're gonna use the data of patenting, like how many patents firms obtain in certain fields, as a proxy for like research, essentially. And even doing so, it's still difficult because we have many different classes of patents, and in fact, the U.S. Patent and Trademark Office, as a one rough classification, uses more than 400 classes, and there are finer classifications for this. So it's very high dimensional. It can be very unstructured, and existing methods may not preserve the shape of data. So we can think, for example, about principal component analysis, which we may know is a linear method. You can think of it as kind of like projecting to a linear space. So if your structure is not linear, this may not be able to capture all the complexity or the interesting shapes in your data. And of course, clustering algorithms can also be limited because you get clusters, but you don't get interrelationships between those clusters necessarily. So before going into the topological data analysis, let's think about what sort of data we're actually looking at. And so here's my data. We have patents granted and patents acquired by mergers and acquisitions. So the patents granted, that's kind of pretty easy to understand. These are the patents that you apply for as a firm, and then you have to get approved for it. For the patents acquired, this is when a firm merges or acquires another firm. They also acquire all the patents or all the technological innovations that that firm has. So in a sense, that's also um, acquiring new patents. So this is also included in our analysis. And later we'll be comparing these sorts of patent performance to actual financial performance. So we also have those sorts of data. But for now, let's just focus on the patents first. So we have data as PITC. This is the number of patents for firm I. We have 333 firms in the year T for these years. And then we have patent classes C from 1 to 430. So just a notation to talk about our data. So, okay, so what does it actually look like? Well, we can try to graph our data for each firm in this way. So fix a firm I, and in this example, I'm showing Cisco systems. I think they're the one that are doing WebEx, another one of the web conferencing software that's getting popular nowadays. But anyway, so we have Cisco systems here. And on the horizontal axis, I'm plotting year T. And on the vertical axis, I'm plotting the patent class C. And I'm drawing circles which are proportional to PITC. So you have a bigger circle if a Cisco system in a certain year, in a certain class, has that many patents. And this is kind of expected. Cisco systems' core business would be in communications. They do routers and so on. So we have lots of patents in class C equals 370, corresponding to multiplex communications. And you also have lots of patents in class 709, giving you multi-computer data transferring, which makes sense. This is nothing too surprising here. We can also think about, look at other firms. So this is Cisco again on the left. Seagate does hard drives and essentially storage systems. So as expected, you have a 360, patent class 360, lots of patents here, corresponding to dynamic magnetic information storage or retrieval. Still also expected, medical related, we have similar patterns for medicines and medical devices associated with surgery and so on. So nothing too surprising. But once you get to the bigger firms, it's kind of hard to see patterns, like at least visually. So we have GE on the left here, for example. It's the most diversified firm among the firms that we've studied. They're patenting in more than 300 classes, and it's really hard to see what's going on. IBM again has the largest number of patents in our study, and so yeah, there's some kind of pattern here, major patenting going on here on these lines, but otherwise, like, it's pretty much distributed in many different classes. So what am I trying to get at is the portfolio aspect, meaning looking at one firm and looking at that firm's portfolio is very interesting and of course contains very important information. But what we want to be able to do is to look at the big picture, to look at the whole collection of firms and see how they interact with each other to be able to like create a map of all the firms in one picture, right? So, but the high dimensionality of this technological space makes analysis difficult. So, in our study, we used Mapper, which maps things. Right. So let's introduce Mapper then. Um, and I'll do this introduction in the as a general introduction. So Mapper is a tool in topological data analysis that is able to extract simplified or the essential shape of complicated data. And once we go through the Mapper procedure, this will become more clear, hopefully. But for now, it's just a way of extracting shape of complicated data. And in fact, there's a company that uses Mapper in combination with machine learning and AI, and that's Symphony AST. If you're interested, you may check out their website as well. But for today, I'll just explain the basics of Mapper. Right, as first proposed in this paper by Singh, Memoli, and Carlson. Right, so the general picture, the overall picture is you have complicated data and Mapper gives you a simplified representation as a graph, which somehow expresses the essential shape of the data. And for this talk, I'll be using this hand as an example. But of course, Mapper can be applied to actual complicated and high dimensional data that you cannot actually draw. If you can draw your data, there's no need to do this Mapper thing because you can just view your data directly. But anyway, so before actually giving the computational details of Mapper, let's give a few examples of applications. So here's one by these people in this research paper, where they were able to identify or discover a new subgroup of breast cancer by looking at this sort of Mapper graph. And so let me explain what's going on here. So they had as data breast cancer and normal breast tissue gene expression data. And what they did as a pre-processing, they computed a healthy state model and tried to compute a deviation from that healthy state model. So this is hard. This may be hard to visualize, but they applied Mapper to this, the Mapper analysis, and obtained this Mapper graph. And what you see immediately is that, or what they saw immediately is that the known groups, you have the normal or normal-like group clustered here. You have your ER positive group here and ER negative. These are the known breast cancer types. And what they notice is that there's this area here where it's surrounded by sparse data, meaning which suggests that it's a subgroup on its own. And looking at this Mapper graph, of course, the Mapper graph does not guarantee any sort of result. You have to go back to your original data and see what's going on here. So they actually did that. They went back and looked at the original data, looked at this subgroup, and what they found was that the group here had molecularly distinct cells with gene expressions with 100% survival for the patients, no metastasis, and has not been identified previously by more classical clustering algorithms. And so they found that significant enough to say that, okay, there's a marker for it, by the way. So they called it the CMYB plus tumors, and that's their new discovery of a subgroup, which was aided by the use of Mapper to identify an interesting region in their data. Here's another example by these people in this research paper, where they took NBA player performance statistics, applied Mapper to it, and what they found is that there's they can give a finer classification of your players compared to the standard 5 positions. Right. So I'm not very familiar with basketball, so I don't want to comment too much on this sort of example. But essentially, what they're claiming is that compared to the standard 5 positions, you can give a finer sort of classification for your players. as evidenced by their performance in game. And here's another example, again in this paper by these people. So you have United States House of Representatives voting records, and for every year they performed mapper analysis and then counted the number of clusters or the number of components in the mapper graph for each year. And they plotted it as a what they call a house fragmentation index for every year. And you get these interesting spikes in, say, year 2001, 2008, 2010, and so on. And it's interesting to see that these years actually correspond to, let's say, contentious political issues, which may have fragmented the House voting patterns for those years. So this is also something very interesting about Mapper. Of course, like, can classical methods see this sort of fragmentation? Well, let's try principal component analysis, for example. And what you see is that in 2009, 2010, for example, you essentially have a divide between red and blue, meaning Republican and Democrat representatives, essentially. And nothing else seems to be out of the ordinary here. Whereas in the House Fragmentation Index, you see 2009, 2010, it's really different in terms of the number of components. So this suggests that Mapper is able to see something more a more interesting structure compared to PCA. So for our work, what we did is to apply Mapper to firms' patents data, and this is what we got. So immediately, the presence of these branch-like structures, which we call flares, is very interesting, and we will talk about this in detail more later. So let's talk about the mapper procedure. There are 4 steps. First, you prepare your data. You choose a filter function, which I'm illustrating here by color. You chop up your data using your filter and some cover, which I'll explain later. And then from that, you create your mapper graph. So first step, you have to prepare your data. In my example, I'll be talking about 3D coordinates. But more generally, you can think about having samples from 1 to n, each of which is represented, or you have measurements of feature 1 to feature m organized as this sort of matrix. Or more generally, you can apply mapper to this sort of data. You have x comma dx is a set of observations, and you don't even need coordinate data for your observations. You just need pairwise dissimilarities captured by this dissimilarity function d for your data. So some particular examples, you can look at firms with, say, financial performance metrics. You can look at cells with gene expressions, and so on. So mapper is very general. You can apply it to a lot of different data. And then the first step is to choose a filter function. Here, I'm projecting my hand onto the horizontal axis, which I'm illustrating with color. And but in applications, we would actually want to try functions that are meaningful for the data, which of course may vary depending on your application domain. So some easy examples come to mind. You could use known performance metrics for your data. You could use dimension reduction, say PCA, MDS, and so on. In general, you have some function f from your data x to rd. In general, we can think about a filter function that goes to d-dimensional space. And the next step is to cover your data. What we mean by that is we take the filter function, we cover its image, and the usual choice is to take intervals or hyperrectangles with the same lengths with uniform overlaps. So example here, we have intervals for our image, And then we pull this back to the original data via taking the inverse function. And this induces a cover of your original data. And what you do is you partition your data based on this cover and your filter function. And okay, you get this partition of your data. You perform clustering, any sort of clustering algorithm that you may want to use in each partition. So for example, here we have 3 clusters for these 3 fingertips. And each cluster we represent by a vertex. And the final step is to draw an edge if there's a non-empty intersection between 2 clusters. So again, let's look at these fingertips. This fingertip has an intersection with this part here, which is represented by this vertex. Therefore, we draw this edge. Similarly, there's an edge between this vertex, and so on. Okay, and if desired, we can color the graph by values of the original function. But essentially, at this point, we have the mapper graph, and that's the procedure. Right. So as an overview, as I mentioned, it's able to extract the shape of complicated data. And how it does this is the following. Essentially, you're doing local clustering. Remember, you're using the filter and your cover to partition your data into small areas. Well, small according to your filter function. So you're doing local clustering in that sense. And then you're recombining all that information, those small pieces, to reconstruct global information by forming the graph, by looking at the intersections. And this is also very nice for computation because one of the expensive parts of this analysis would be clustering. And since you're only doing it for local regions, it's cheaper than doing clustering for your entire data set. Mathematically, you can think of mapper as a discretization of your Reeb graph. I won't go into the details here. But the main point I want to emphasize here is that this is a tool for exploratory data analysis. What do I mean by this? Well, you have lots of different parameter choices for your construction. You have choice of your filter function, choice of your cover, choice of your clustering algorithm. So what I'm trying to say is that you try out different parameter choices, and then you let mapper point out regions of potential interest. So you go back to your original data and see what's actually going on there. So the main point here is that the mapper graph is not and should not be the final result. So that's it for a quick overview of mapper. Let's go back to talking about firms patents. So again, a quick recap. We have data PITC, which gives the number of patents acquired by firm I in year T. That is corresponds to patent class C. We can organize these as vectors PIT, and then we do some sort of smoothing and log transform. And then we organize our data in this way. We want to view time evolution spatially, essentially. So we're looking at points as firm years, pairs of firm and year. So firm I and year T is the data XIT corresponding to that firm I and year T will be considered as a point. And for example, well, IBM in year 2000 will be considered as a different entity as IBM in year 2001. So we're scattering the different time observations spatially, essentially, in one graph. And so this is how I'm treating my data. And here are the details for the mapper parameters. As a filter function, I'm using principal component analysis and projecting in particular to the first 2 principal components. For my cover, I'm using the default implementation in this software for mapper computation, which means 20 by 20 grid of rectangles with 50% overlap between neighboring rectangles. And for clustering, I'm using single linkage hierarchical clustering based on cosine dissimilarity, which is defined this way. And this is a dissimilarity function that's commonly used in the patent literature. So we also use this metric. And we use the first gap heuristic for determining the number of clusters. So we need the hierarchical clustering gives you a dendrogram. You need to cut it somewhere. And so we have this heuristic, which is from the original mapper paper. So we're just using that heuristic. So I think I've showed you this the mapper graph already before, but here we've added labels corresponding to major industry types. Let's zoom into the IT region here. Oh, by the way, I should say this division into industry types is not imposed on our side. It comes from the data. So this is pretty much what the data looks like as is. Well, after applying mapper. So let's zoom in at the IT firms region. So we've added lots of labels here, and let me explain what those labels means. So recall that in general, the vertices of the mapper graph are clusters. So from general principle, they are clusters. They should contain different firm years. But some clusters have only one, one firm year or firm years associated to the same one firm. So in those cases, we just label that cluster or that vertex by the firm name. So for example, we have the label Robert Bosch here. This means that the vertices here in this mapper graph contain only the firm Robert Bosch. And that's very interesting because that means essentially that these firms that are shooting out from the central part of the mapper graph are not, in some sense, intuitively, they're not close to the other firms. That's why they get their own cluster. And these sorts of branch-like structures where the firms are, say, um, taking their own unique paths, we call as flares. And we also have peninsulas that are of interest. We have similar observations for the other industries. So we have here medical industries and materials. Again, we have flares. So let's actually give a mathematical definition for flares. So first step, we want to look at a fixed firm I. We define its region as the full subgraph with vertices, i.e. clusters, containing or not containing only, but at least containing firm I. Is that correct? Yes. So we restrict to the region of the mapper graph that is involved with firm I. And then what we do is that we say, okay, that's the region of the firm I. The interior of the region is defined to be vertices that have no neighbors outside the region. And the boundary would be defined as vertices that have neighbors outside of the region. So in this example, here we have the whole mapper graph. Here, let's assume that we have some firm with this sort of region. The green vertices are the interior and the purple ones are the boundary. And flares are we simply define as and islands we simply define as connected components of the interior. So here we have two flares, and an island would also be a connected component in the entire graph. So two flares, one island. And okay, we still need to measure how large these flares or firms are. So we give this definition of an exit distance. So for a certain vertex u in the interior, the exit distance is just the shortest path to get out of the interior, and it's defined this way. The problem with this definition as is that we need information about shortest paths in the entire graph. But with a bit of math, you can show quite easily that actually this exit distance can be computed as the length of the shortest path restricted to the region I to a point in the boundary, which makes sense because intuitively, to get outside of the interior, you need to pass through the boundary. And as an observation, this exit distance can now be computed using only the shortest paths in the region of I, which is smaller than the entire mapper graph. So we use this for actual computations. Right. So we have this concept of the exit distance. The flare index will simply be the maximum exit distance. So in this example here, this flare here has flare index 3 because the farthest exit distance would be this point. You have 1, 2, 3, and then you're out. So this would be flare index 3, flare index 1. This one has flare index infinite because you cannot leave the island. Right. So to evaluate the relevance of these flares versus actual economic performance, we do this sort of linear regression. So here we have as a variable yi firm i's log revenue in the year 2005, which is the last year in our data set. And then we have these terms. So ki would be firm i's flare length with some coefficient. And assuming this is finite. If it's infinite, meaning it's an island, we put a dummy variable, a Boolean variable ki equals infinity, representing ki being infinity for islands. And we also put in our linear regression the firm i's total patent count over all years and all classes here. So the point of putting this in our linear regression is to factor out the effect of total patent count, because it makes sense that larger firms would have more log revenue and more total patents. So kind of putting this here would try to reduce the effect of having this this linear regression essentially explaining that total more patents means more revenue, because we want to actually isolate the effect of the flares. Right, so here's a graph of the data we have on the horizontal axis, flare length versus log revenue. It makes sense that it's this way. And here are the regression results. So column 3 would be the full model where we incorporate all the variables here. And what we get is that we have positive coefficients for flare length and islands only. And here we have 0.34 coefficient, which means that flares are correlated with this e to the 0.34 minus 1, or 40% higher revenues. And to check that actually this makes sense, we also put here the restricted model, where we forcibly put flare length and islands to be 0. And this is the explanation here. F-test of the restricted model, meaning column 2, gives us that we should reject the null hypothesis at 0.01%, meaning that the contribution of the flare and island variables are statistically significant. Right. And there's okay. So there's that. I also forgot to mention that looking at this graph again, it's interesting that so higher flare length is correlated with more log revenue, but you can have big revenue without having much flare length. So what this suggests to us is that, well, it also makes intuitive sense that flare length doesn't capture everything about the firm's performance, and there are other aspects of uniqueness of firms' activities that cannot be captured by flare length. But at least if you have more flare length, then what you can say is that you are correlated with more revenue. Again, we are not saying a cause and effect relation here. This is just a correlation study. So to summarize, we can represent from stock technological locations via the mapper graph, and we can measure the flares of each firm in this graph, and well, results suggest that this contains relevant economic information. Thank you for your attention. Are there questions?
Okay, thank you very much. Now we are welcome to your questions and comments to Emerson. I think now I'm sharing the AIP Open Seminar web page, and next one will be scheduled on November 25, so the next week, on the about geoinformatics unit by Yokoya-san. So we hope you will join again the next week. Right. So this is the end of today's seminar. So again, thank you very much for joining. And yeah, thank you.